This podcast is brought to you by LMU Munich.
Yeah, welcome back to the fourth and last part of the introduction to higher spin gravity. So let me first remind you what we did the last one or two lectures. So we saw that it is very convenient to formulate higher spin gravity in terms of a Chern-Simons theory in 3 dimensions. Because it turned out, we already know, that spin 2 gravity can be formulated as such a Chern-Simons theory of this form, like k divided by 4 pi times the Chern-Simons form of a gauge field A minus the Chern-Simons form of a gauge field A bar. And for spin 2 gravity, basically A and A bar, they lived in the Lie algebra SL2R. And we also analyzed in detail the asymptotic symmetry algebra, which turned out to be 2 copies of an Virasoro algebra. So this was just for spin 2 gravity. What we did then is we looked at the kind of simplest extension we can think of. Namely, we added just a spin 3 field to this spin 2 gravity. And this was done by just allowing A and A bar to be not just in SL2R, but in SL3R, in the Lie algebra SL3. And it turned out, so this really describes spin 2 plus spin 3 gravity in some sense. This statement is true, so that it really describes spin 2 plus spin 3 gravity. If we embed the SL2R subalgebra in a certain way into this SL3R algebra. So this is what I called principal embedding. And then it turned out that the asymptotic symmetry group is an algebra which you might also see in the talk by Matthias Gabedil next week, which is referred to as W3. We can continue this, so an obvious generalization is if A and A bar is just in SL NR, so then we couple just the spin 2 up to spin n degrees of freedom. And the asymptotic symmetry algebra is then instead of W3 and Wn plus Wn. And again, this will be covered in Matthias Gabedil's talk. So basically now, last time we stopped because what we wanted to achieve, we don't just want to couple a finite number of spins with each other, but we want to couple infinitely many spin fields with each other, like from spin 1, 2, 3 up to, say, infinity. So how do we do this? And so spin 2 up to infinity. So this is done by A and A bar living in an algebra which is known as HS lambda. And we stopped last time by discussing the definition and of this HS lambda algebra. So let me add a few more things. So definition of HS lambda. So we do not look now just at HS lambda, but I look at an algebra which I call B mu. And B mu is basically the following object. It's the universal enveloping algebra of SL2. And we divide out by a so-called ideal So it's C2 minus mu times the 1 operator. So first, what is this object here? So this object is just the following sum. Basically, we look at sums of one operator plus, say, alpha I, ji, so these are the SL2 generators, plus, and now we also look at products, let's call it the coefficients alpha I, j, of products of SL2 generators, like ji, j. And usually such products of two SL2 generators are not contained in the Lie algebra SL2. Only like Lie brackets of generators are again contained in the Lie algebra. And so on. We also look at cubic ones. And so on. So this is what is known as this enveloping algebras. And so basically this denominator here says to me that a certain quantity, C2, which is the so-called quadratic Casimir operator, and can be written as J0 squared, so J0, J1, and J minus 1 are the generators of SL2. As this object here. So it's quadratic in the generators, and that's why it's called quadratic Casimir operator. And so basically this ideal here contains of like polynomials in C2 minus mu times any other polynomial in the generators. And so what this here says is that you look at such an arbitrary polynomial, and whenever you see basically such an expression here, C2, you set it to mu times 1. Okay? So suppose you just have this polynomial, and this polynomial, of course, is of this form here. Then, in this B mu algebra, this polynomial will be just replaced by mu times 1. Okay, so this is the definition of this B mu. And now the question, how is this B mu related to HS lambda? So first, I have to tell you that this mu value is somehow restricted, because what we want to have a unitary representation, and unitary representations of SL2R, or SL2, have the property that C2, so this quadratic Casimir operator, is larger than minus 1/4. Okay, and so you see the C2 is precisely, or is equal, if we divide out by this ideal, with mu times 1. So therefore it's convenient to set, so mu has to be larger than this minus 1/4, and so we can write mu as 1/4 times lambda squared minus 1. And for any value of lambda, this mu is then larger than minus 1/4. Okay, in particular for lambda equal to 0, it's precisely 1/4. Okay, and now I define h as lambda, because we can, in this case, we can therefore write this b of mu with precisely this relation between lambda and mu just as the algebra h as lambda plus plus 1. So you see in this b mu, here the 1 is contained. And this is not part of the algebra h as lambda. Okay? So basically h as lambda corresponds to the generators, like to linear combinations of the ji's. Of course there are quadratic ones, cubic ones, and so on, fourth order ones. But what you do at the end is you set, then whenever you see such a linear combination, you set it just to mu times 1, where mu is basically this value here. So this is the definition of this higher spin algebra HS lambda. So why is this higher spin algebra then so important? In particular, you can ask yourself, are there any special values of lambda where we know the algebra already? And it turns out that if you put, or if you set lambda to be n, then in some sense, and I will explain to you what this word some sense mean, this algebra HSN reduces just to SLN. Okay? So for lambda being to n, HS lambda is related to SLN. And to be precise, what this means is it turns out that all the spins, all the generators of HS lambda, which have spin larger than n, they basically decouple. So all generators, and these generators I denoted last time as VMS, with S larger than n, satisfy, if we have lambda to be n, that the trace of these operators VMS and VNR, and VNR is now an arbitrary one, so R does not have to be larger than n, is equal to 0 for S larger than n. And so that's why basically we can write then SLN just as being isomorphic to HS lambda, where we again divide out by an ideal, and the ideal are basically now all these generators, VMS, like the higher spin generators. Yeah, so this notation just means, suppose you have HS lambda, and, sorry, HSN, lambda is of course n. Then basically you just view the generators with spin S being n or smaller. In other words, all the other generators are just set to 0, so they are not there. Then you get back SLN. Okay? So in particular, for any value of lambda, which is not an integer, we cannot do this. We cannot reduce it just to SLN. And you may view then this kind of HS lambda as being something like SL infinity. Okay? Where you have basically infinitely many generators. Okay. And so really these A and A bar, they live in this HS lambda. And again, we can determine now the asymptotic symmetry algebra. And since we couple infinitely many spins, it's a W infinity, or what's referred to as W infinity, but also this lambda has to appear, plus a W infinity of lambda. And this is again also an algebra which will be introduced by Matthias Gabediel. Basically, he will look at CFTs precisely with these symmetries, and these CFTs with these symmetries then just correspond to an higher spin theory with this strange HS lambda higher spin algebra. Yes?
So do I fix the value of lambda, or do I get different theories for different values of lambda, or do I keep it arbitrary?
So very good point. So we have basically a mapping from the CFT to this gravity theory for any value of lambda, in particular if lambda is being 0 and 1. And you will later see on the CFT side that this lambda somehow corresponds to a kind of a coupling constant. It's more or less like a Toft coupling constant. And you will see how this lambda really appears on the CFT side. So it comes from a so-called coset symmetry, coset CFT, and you will see that basically lambda is a quotient of like, say, the affine parameter k and rank n. Okay, so it's an interesting question, but within the framework of this lecture, I cannot answer it, so I just hope that Matthias Gabriel will do it, because he also came up with this relation. Yes, it gives you different ones. Okay. Good. So, but all of these gravity theories, they have one drawback. And the drawback is, or also the nice thing, to be honest, they can be formulated in Chern-Simons theory. And what are the equations of motion of a Chern-Simons theory? We already wrote them down. The equations of motion are basically that F, the field strength tensor, which is dA plus A wedge A, has to vanish. And also F bar has to vanish. And so this means it's in some sense pure gauge, so you don't have any propagating degrees of freedom. You don't have any plane waves. And this is consistent with the three-dimensional gravity theory, because also the three-dimensional gravity theory, if you just count the degrees of freedom, then you will see there are 0 degrees of freedom in it. So it's kind of topological. That's what. So the question really is, can we add something which has propagating degrees of freedom? Can we, for example, add a scalar field? Because then it would be interesting. Then the theory is also dynamical. And this is a very interesting question. And this precisely leads to chapter 5. So which is basically higher spin gravity part 2. And you can view it as coupling matter to higher spins. And this will be a very brief chapter. If you want to know more details about it, please ask me. I will be also around next week, so we have plenty of time. So this formulation of higher spin gravity is, which I will discuss now, is due to Vasiliev and collaborators. And they worked on it like the last 20 years, so there's a lot of literature. And to be honest, if you first see this Vasiliev theory, then you think it's a mess. And also later on, you will always think it's a mess. So therefore, let me just be a bit brief and let me just discuss the field content and a few interesting features. So the field content is we have massless higher spin fields. So S, 2, 3, 4, up to infinity. So we have infinitely many higher spin degrees of freedom. and I want to write down here something, and we have massive scalar fields. So, and these massive scalar fields, they don't sit in the multiplet of the higher spin fields. So this has two advantages. First, we can set the scalars to 0 and just look at the simplified version. And the second advantage is that these scalar fields, they can be massive. Okay, good. So how do we link the massless higher spin fields and these massive scalar fields to what we know from the Vasiliev equations? So basically in the Vasiliev equations, we have three ingredients. It's a space-time one form, which is called W mu. We have a scalar, which is called B, and we have something which is called S alpha. This is also a one form, but this one form lives in a kind of an auxiliary space. Okay? So we have to add, besides our space-time variables, we also have to add other auxiliary coordinates. For example, like in superspace, we also add to our space-time variables also the fermionic variables theta. And here we also have to add we have to add auxiliary variables. And S alpha is basically just in one form in this auxiliary space. So the nice thing is that this W mu, this corresponds really to these higher spin fields. And in our notation, we would split this W into what we refer to as A and A bar. Okay, so this W mu is nothing else than the geometry than the higher spin fields. What about this B? So this B is already a scalar. So it might be the massive scalar field. And this is true. If we split B, so what we do is we make a split into nu plus C. So this is basically the constant piece at infinity, which we, for all the, basically the overall constant is split off. And C is just then a scalar field. So this parameter nu here is related to lambda. In the way that nu or lambda is given by 1 minus nu divided by 2. So whenever you know nu, then you know lambda. If I know lambda, and this is the nice way, it's a bit recursive, then I also know in which gauge groups the A and A bar live, namely they precisely live in this HS lambda. But this lambda is determined by the constant piece in B. And this has to do because in these Vasiliev equations we have certain constraint equations which tell us precisely this information. So what about this S alpha? They are auxiliary fields. And I really dream to integrate out these auxiliary fields, just to have like W and W mu's and B's. And this would be a nice formulation of the Vasiliev system. But so far this is not available. Okay. Just to get an idea how difficult this is, so the C does not live in HS lambda, but it lives in this algebra which I call B mu. Okay, probably I should relate the mu to lambda, so in this equation you might think, okay, this relation between mu and lambda is always here implied, this one here. So C lives in this B mu, which is just a function of lambda. And precisely the one component, so this component here, not the higher spin ones, but this component here, I would denote by C0. And this C0 here is described by a Klein-Gordon equation, as we expect from a scalar field. And the mass, sorry for that, there's a relation between the mass and lambda of the form that the mass squared is equal to lambda squared minus 1. So in particular, you see that lambda could be 0, so the mass squared could be negative. But this is not a problem, because in entity zeta space, and here we are working entity zeta space, you can have negative mass squares. However, they have to be above a certain limit or a certain number. This is this bound, and this is the so-called Breidenlohner-Friedman bound. And in 3 dimensions, the Breidenlohner-Friedman bound is precisely minus 1. So this makes sense to look at such scalar fields with mass larger or equal to minus 1. Mass squared larger or equal to minus 1. Okay, so this is just the field content. What about the equations of motion? And they are really complicated, and I don't write them down. If you really want to know more about it, I can give you literature. We can go through the Vasiliev papers, can explain to you. The problem is, even I've written down that we have auxiliary fields and the rest. This is not completely true, because also the scalar fields and the higher spin fields, they have auxiliary parts. It's a highly complicated system, and in particular the scalar fields and the higher spin fields, that's an infinite sum, because it lives in H's lambda, so it's an infinite sum of generators. However, what I want to advertise is that if you just want to look at a scalar field propagating in this higher spin background and not backreacting to the geometry or not self-interacting, so in kind of probe limit, the probe limit of scalar fields is basically given by the following equation, which is very, very nice because it can be expressed totally in terms of A and C. Star just means this is just the multiplication rule of the two generators of H's lambda, so it's nothing fancy. So this is just the equation of motion in the probe limit. So if you basically just look at basically scalar fields which do not backreact to the metric and which are not interacting, and which are not self-interacting. Okay, so this is the Vasiliev equation, and later on this equation might be important again. So I didn't add now kind of gauge degrees or like an UN gauge symmetry, which you can also do. Vasiliev did it. So what we know is we only know so this is, by the way, probably something which I should have highlighted here. What we only know, and what I've got only given to you, is basically just the Lie algebra, H's lambda. I didn't talk anything about the Lie group, whether it exists or not. This is also a problem in the math literature. We don't know too much about the corresponding Lie algebra, if it exists and what are its properties. So important is that the gauge fields A and A bar just live in HS lambda, while the scalar field, it lives not in HS lambda, but it lives in this B mu, which is only related through this construction here. No. Okay, very good question. So the question was, can we truncate the infinite tower and just have a scalar degree of freedom? So this is very, very complicated. And so in this Vasiliev formulation, this is impossible. At least the scalar would be non-propagating. It would be not dynamical. Yeah. Of course, if you want to have a non-propagating scalar, then you can do it. But okay. The interesting part is like a propagating degree of freedom. So there was another question.
What does the star mean?
Okay. So the star is just basically here A and C. Both of them have these HS lambda generators, or an 1 in it. And now I have to multiply two of these HS lambda generators together. And so the multiplication rule is denoted by star because it can be rewritten as a kind of a Moyal product, or a generalized Moyal product. Okay? So that's why it's always referred to as star. So it's just like the multiplication rule of one HS lambda generator here and one HS lambda generator here. Okay, just write down dot if you don't like the star.
Is this massive scalar for the classical one or?
So far we are just talking about classical gravity. But we hope to be able to quantize that system. However, in a very indirect way, and this will be done or will be discussed hopefully by Matthias Gabardel, we can map this whole system, the classical version, to a kind of large n limit of a conformal field theory. We can solve the conformal field theory, not only for large n, but also for finite n. But then for finite n, it corresponds to a quantum Vasiliev gravity theory. And so we can make predictions for quantum gravity in these higher spin gravities setups. Okay. Further questions about this Vasiliev system? Yes? Yeah, but okay. So this W mu is, so this mu just refers to that W is basically, it's in one form. Okay. So this is something like your A and your A bar. However, each of these components also live in HS lambda. Okay. And just think about lambda being n. So each of this component is an SLN generator. Okay? And now we have the usual prescription how to get the metric, at least for SLN, how to get the metric spin 3, spin 4, spin 5 fields, and so on. What we do is from A and A bar, we calculate the spin connection and the field bind, because A and A bar is something like spin connection plus or minus field bind. So by taking the difference of A and A bar, we can calculate the field bind, and then we just compute the trace of E mu E nu, and this will give us G mu nu. Or we calculate the trace of E mu E nu E rho, this gives us the spin 3 field, and so on. Okay? So all these spin fields, massless higher spin fields, they are encoded in this W mu in a very indirect way. Yes.
It is consistent. But is it possible, or there is any kind of workaround not to couple, for instance, massive higher spin to higher spin? I mean, is it possible to couple massive gauge field to this?
In principle, it should be possible. But I think the people just looked at the massless case. Okay, so good. So the scalar field here lives in this B mu, okay? And this B mu is like 1 plus hs lambda. So this is just the scalar component of my scalar field. But also the scalar field also has higher spin fields associated with it. Okay? Just think of the scalar field phi. So this is your original scalar field. And then you just get a vector out of it if you just look at, say, d mu phi. Or at a combination like phi d mu phi. Yeah? And trace phi d mu phi. This would be a spin 1 current made out of a scalar field and so on. So in principle, I guess you can do this and generalize this. Further questions? So, like, second to last row? Oh, good. Very good question. Equations of motion, I didn't write them down. There are 5 equations, or doesn't matter. Depends how you write it down, which fancy way. But they are just differential equations. So far, there's no action principle known. Okay? Also for this, all the higher spin gravity theories, which I discussed here, except the very second line where A and A bar is SL3R. I told you there we have a proposal for an action, however, only to second order in the spin 3 field. And even we can't go to fourth order in the spin 3 field, not because it's impossible or we run into some conceptual issues, but only because of the computational complexity of the problem. Yeah? So the mathematiker doesn't want to calculate it for you. So you need a better trick. Okay, so my guess would be, if you want to work in this direction, first try to calculate it for higher spin gravity where just couple in spin 3 field with a spin 2 field. Then try to generalize it to like SLN case, and then first try to then generalize it to hs lambda, where you set the scalar field to 0. And this is, of course, already an achievement. And at the end, then let's hope that you get also a proposal for the Vasiliev system. Okay? But so far, we don't have an action principle for all these theories. And this would be nice to have an action principle, because then it might tell you also a bit more about how to get rid of these auxiliary fields. Yes?
Why is Doro constant free?
Sorry?
Why is Doro constant free?
The log? No.
Doro constant.
Of the 1 here? Of C0? Oh no, of nu here?
Yes.
So yeah, basically, so you have a theory, the Vasiliev equation can be formulated right at the beginning without making any reference to hs lambda. Yeah? So basically, the Vasiliev theory dynamically picks you which lambda you're looking at. And that's precisely, say, this overall constant factor. So suppose you have a scalar field, say in x direction, which looks like, so this one here. Then first you want to cut away, so this constant, which you would call nu. So that at finity, this scalar field approaches nu. And so this defines your nu. And the rest is called c. And this nu, by looking at the constraint equation, then tells you that S alpha has a certain value, and if S alpha has a certain value, then you see that the W mu or A and H bar have to live in hs lambda. And nu and lambda are precisely related by this way here. So in some sense, Vasiliev theory makes it say to you dynamically which gauge group you have. So let me compare this to something you know in string theory. Suppose we write down some kind of string field theory in a very generalized form, yeah, for open and closed strings, for say type 2a or type 2b string theory. But I don't make any reference to how many d-branes I put into this system. Only after I put into the system, I know that there is a new UN symmetry generated if I have coincident d-branes, for example. But beforehand, I didn't know anything about this gauge algebra. And in this sense, also this is a bit, probably not the same, but it's a bit similar in its spirit. That basically, beforehand, you don't know anything about this gauge group, but then if you start solving that theory, this is dynamic, or this, you see that there's only one possible choice, namely HS lambda. And you can calculate lambda. Okay, further questions? Good. So then let's go on, because I want to talk about another fascinating subject. So far we looked at higher spin gravity theories and simple solutions, mainly ADS or Poincaré, like ADS in the Poincaré chart or ADS in the global coordinates. But what about solutions which look like black holes? So basically chapter 6 is higher spin black holes. And just due to the lack of time, I restrict myself to the simplest case, like to spin 3 higher gravity. So Chern-Simons theory with SL3 times SL3 Chern-Simons gauge algebra. So and before I look now at such a higher spin black hole, I want to show to you first how the BTC black hole, which is also present just in usually Einstein gravity with negative cosmological constant, how the BTC black hole arises. So this BTC black hole has no higher spin charge. So it's just a spin 2 object, basically. And so the gauge connection for BTC, and we've already seen the most general form, looks like this. It's an e to the row J1. And this should be now familiar to you. So there's an L of C in it here. So this is just the most general form, and I'll tell you later what this L of C is, precisely for BTC. And A bar is given the same way, where J1 and J minus 1 are, and J0 are just the generators of the SL2 subgroup or subalgebra inside SL3. So this is the gauge connection. And now, again, if you subtract them, like A divided by A minus A bar, then you can determine the field bind. Then you just multiply 2 field binds together and take the trace, you get the metric. Okay? And you see that provided I set L of Z to be constant, and the constant is precisely given by this, it's an M L minus J, where L is the characteristic radius of the asymptotic ADS spacetime. And L bar of C bar should be also just a constant. It's also 1/2 ML plus J. And M is just the mass of your black hole, and J is the angular momentum. So it's rotating. And from now on, what I will do is I will set small l to 1 and J to 0. I just want to present to you the simplest case. Okay, so L and L bar are even the same. They're just given by the mass divided by 2. And you can now really, as an exercise, just compute the metric and the spin 3 field. And you see that the metric just has an event horizon and a singularity, at least if you do a coordinate transformation, and that the spin 3 field vanishes. Okay? So later on, what I will need also in a higher spin case, and I will generalize this in 5 minutes on higher spin black hole, I don't want to use this capital A and capital A bar because I'm always lazy about the row dependence. So I told you last time a trick to get rid of this row dependence, namely by using a gauge transformation. And the gauge parameter, again, is given as b rho as e to the rho times j0. And if you do this, then you can relate your A BTC to this way. And also the A bar BTC. And I write down both transformation laws because now to make some things a bit more apparent, I changed one of my sign conventions, which is just a sign convention. So here, basically, the A bar, the minus sign, so basically I redefine what I mean with A bar. And if you do this exercise, this gauge transformation, then you will end up with A of BTC. So you just lose the row dependence. Yeah? So you set just row to 1, basically. Okay, so this is A and A bar. So, as I said, this is just a gauge transformation. So, certain objects like holonomies or Wilson loops, they don't change their value if you do such a gauge transformation. And what we will look at now, and this might be not so clear or apparent from this discussion here, but it will be very important later on. We will look at the holonomies. In particular, we have a black hole, so this corresponds to a finite temperature state. So what we did is we compactified our time-like direction on a circle. So okay, we have now a circle along the time-like direction. So what I can calculate now the holonomy associated precisely with this circle. And the time-like circle, so basically our tau, our Euclidean time, is compactified like on a circle with circumference beta. So what we do is now we calculate basically the path-ordered exponential of, along this curve C, of A mu dx mu. Okay, so this is an holonomy. And I call this now just e to the omega. And omega is a 3×3 matrix, because here this A mu is a 3×3 matrix. It lives in the Lie algebra of SL3R. Okay, so but let's look again at this. And so A mu, this is, okay, now I'm running out of, so this is the BTC connection. the one which I wrote down. But let's look at this connection a bit closer, and particular, let's see if it's constant. And you look at just this connection here or here. The only thing which might be dependent is L or L bar, but since we look at a BTC black hole, L and L bar are constant, and the constant is given just by the mass of the black hole. So basically, this gauge field is now constant along my time-like circle. So this means that I can forget about the path ordering, and that I can immediately perform the integral. And what I get is the following. So this here is just the exponential, and I want to perform it now along the time-like circle. This is AT times beta. And beta is just, so like if I go once around, so AT is constant, so I can pull it in front of the integral, and the length of the circle is just beta. So in other words, I know that omega is A tau times beta. And if I remind yourself now what tau is, so tau was this Euclidean direction, and we defined C to be phi plus I tau, and C bar was phi minus I tau. And then you can convince yourself, so I want to transform now this A tau into an AC and an AC bar. And so what you get is the following. You get an I beta times AC minus AC bar. So this is just the C component multiplied by DC, and this is the component multiplied by DC bar. And you can write this in a bit funnier way even. You can write this as 2 pi. This is the formula which I will use later on. Tau times AC plus tau bar times AC bar. Okay? And tau is just I beta divided by 2 pi. And here this minus sign is lost because here I've written down tau bar, since this is purely imaginary, taking the complex conjugate, and here it's really the complex conjugate, is given like minus I beta divided by 2 pi. Okay? And so what you can do now is you can compute this holonomy for the BTC black hole. So for the BTC black hole, omega has eigenvalues 0 minus 2 pi r. Okay, so I can represent it in a convenient basis. Doesn't have to be the original one. I can represent it as this matrix here. It's just the eigenvalues sitting on diagonal and otherwise 0. And in other words, I can reformulate this. I can look at e to the omega, and e to the omega is just 1, 1, 1. So the unit matrix, which of course is in the center, which I call C now, of SL3, of the Lie algebra SL3. Lie group now, of the Lie group SL3. In other words, the holonomy associated with the time-like circle in this BTC black hole has to lie in the center of the gauge group. And this is just checked here for the BTC. Of course, this statement is true because there is no other non-trivial black hole in this 3D higher spin gravity with just spin 2 degrees of freedom. Okay, and this condition will be very, very important later on. We will refer to it as the so-called holonomy condition. So okay, so this was just the higher spin, so this was just spin 2 gravity, so let's do it for higher spin. Higher spin black hole. So the idea is, and this is very important to emphasize, that we want to construct now higher spin black holes, which may be viewed as a perturbation of just the BTC black hole. So later on, what I will introduce a parameter mu, which will be later on the spin 3 chemical potential. And if we set this parameter mu to 0, then I want to recover BTC again. So in other words, so far I'm restricting myself just to higher spin black holes which are continuously connected to BTC. Of course, there are also other ones, but let's discuss this first. So immediately starting from this gauge connection here, and now I just write down the one with A and A bar, I can now generalize it for this higher spin black hole. And so the proposed gauge connection in terms of A and A bar is, again, I just copy parts of this because this has to be reproduced. And so this appears L and also W. We have now two independent variables here. And there also a mu appears here. So this is the gauge connection for A, for the higher spin black hole. Yes?
You said that you are doing classical field theory, but now you said that you have a Hawking temperature. So how does this go together?
So far I didn't tell you anything about the Hawking temperature of that black hole. But of course, like the black hole might be just a classical object, or we can view it as just a classical object, which is characterized by mass, angular momentum, and so on. Yeah? But if we now consider quantum fields on top of that background, then basically we get this Hawking temperature.
I mean, when you're complexifying the time-like direction to a circle, this doesn't mean that you have a temperature.
In some sense, this is, so this is a trick how to calculate the Hawking temperature. What we do is then we just say that our black hole, if we now do a Wick rotation in the time-like direction, so if we Euclidenize it, is a smooth manifold. In particular, it has no conical singularities. And you are right, from such a condition, you can calculate the Hawking temperature. I'm still in a classical field theory. Just think of it as a Euclidean manifold, which is smooth. Okay? Good. So let me also write down A bar. So A bar is given as minus j to the minus 1 minus L divided by k, j1 plus pi divided by 2k, w minus 2 plus 4 pi w divided by k times j minus 1. And so this j and w matrices I really gave you last time. So you can now easily compute also the metric from this gauge connection I give you. So these are the two gauge connections, A and A bar. And you immediately see, if we take the limit mu going to 0, then the second line vanishes here, and also this line also vanishes. And this was one of my conditions. I said it should be connected to the BTC black hole. What also has to happen is also that this W then goes to 0. Okay, but first, before we write down the conditions for the black hole, let me discuss to you what's the meaning of the different symbols. Yes, so this 4 pi W. No, sorry. I guess yeah. Sorry. This should not be there. I think I went one line down. Thanks. Okay. Good. So this is A and A bar. And so what is mu? Mu is just the chemical potential of the spin 3 field. What we also have hidden in this formalism is beta, because beta is just like we have a time-like direction which is compactified on a circle, and the length of the circle is just beta. What we also have is we have the two functions L and W, which we have to determine. Okay, so what is W? W is just the spin 3 charge of the black hole. And L is the spin 2 charge, or like the VEF of the energy momentum tensor. So this is the VEF of this spin 3 field, and this is the VEF of the energy momentum tensor. Like, you can call it spin 2 charge if you want. Okay, so we have 4 parameters, namely mu, beta, L, and W. And what we have to find is, okay, so first what we do is we define alpha to be just tau bar times mu. And again, let me remind you what tau bar is. So tau was just I beta divided by 2 pi, so tau bar is the complex conjugate. It's minus I beta divided by 2 pi times mu. Okay, so beta and mu are just contained in alpha. So I can look now at the system with 3 parameters beta, or say tau and alpha, and I have to determine L and W. So W and L are functions of tau and alpha. Okay, so basically the spin 3 charge should be a function of tau, which is the temperature, and alpha, which is a combination of the temperature and the chemical potential. And also L should be such a function. But the question is, how do we determine this function? So let's make a wish list. How these functions should look like. So how should they be related? And so it's not really a wish list, it's really something which should hold. So first of all, by construction, for mu going to 0, I told you I just want to construct black holes which are perturbative or which are connected to the BTC continuously. So for mu going to 0, we imply that also W as a function of tau and alpha or tau and mu has to go to 0. This is by construction. So this is the black holes we want to look at. So the second thing is, we have here 2 gauge connections, and we can calculate now the spin 3 field and the metric. So the spin 3 field and the metric of the Euclidean solution so after a Wick rotation should be smooth at the horizon. So first there should be a horizon and both fields should be smooth at the horizon. Okay? And the third thing is so that we want the following integrability condition. And the integrability condition tells us that the derivative of w with respect to tau should be equal, at least if we normalize tau and alpha in a certain way, to the derivative of L with respect to alpha. Okay, so where does it come from? So the hope is that W and L are just the vacuum expectation values, say, of the energy momentum tensor or of the spin 3 field. And so we hope that we find an associated partition function such that W is up to certain normalization factors. So let's put a similar sign here. The derivative with respect to alpha, while L is the derivative with respect to tau. Okay? So this always has to hold, because in the partition function you might have terms like so an exponential like times tau times L plus alpha times W. And if you take derivatives with respect to alpha, as you are used to, for example, in quantum field theory, then you generate vacuum expectation values of this spin 3 field, and this is denoted by W. Okay, and so you see the second derivative of C with respect to alpha and tau should be the same. So the W by d tau is d squared C by d alpha d tau, so a second derivative, and this has to be the same as dl by d alpha. So this really comes from that we have an underlying partition function. So these are three very, very reasonable points. Unfortunately, we don't find. So let's start. Let's assume number 2 is correct. Okay. So we have an horizon. We have a smooth geometry. Or let's try to find the horizon. So if we impose 2. Then we can show that 1 and 3 are not satisfied. Okay? And we can even calculate this. The metric of, say, the Euclidean black hole is given in the following form. So it's in d rho squared, and you can really easily calculate it just from the gauge connection, times a function f of rho d tau squared plus a g of rho d phi squared. And I don't give you now the precise form for g rho, I just tell you that this is larger than equal for any value of rho. But let me give you f of rho. So f of rho is 2 mu e to the 2 rho plus pi divided by k w e to the minus 2 rho minus 2 mu over k squared L squared e to the minus 2 rho squared plus another term, which is also quadratic, so it's e to the rho minus 1 divided by k L e to the minus rho plus 4 pi mu divided by k w e to the minus rho squared. So this is f. You see, it's a sum of two terms, both of which are positive or 0. Okay, so the question is, can we have then horizon? And if there's an horizon, then f has to be, because there's no function here in front, so f has to have a double 0. And it turns out you can easily computate it. This has a double 0 for if k and if L and W satisfy the following equation. So k plus 16 mu squared times 2 pi mu W minus L has to be 0. Okay? So if this is satisfied, then we really have a double 0 for f of rho. This is a simple exercise to show, so it's just 2-3 lines. Okay, so you see something interesting, that if you take now the limit mu going to 0, that you cannot satisfy this equation here. So otherwise you immediately see that number 1 is violated. You also see you can solve this equation now, like you can write a w of mu and tau and an L of mu and tau, or you get another condition from here. You can solve it and can see that the third item is not satisfied. Okay, so in other words, either we don't have a partition function of the dual CFT, which is very strange, or something is wrong. We haven't understood a point here. And the point is that this, what we have here, is not really a black hole. But it's also a black hole. So what does it mean? So this metric, if we want to assume that 1 and 3 holds, does not have an horizon, does not have a singularity. But we have a charge assignment which perfectly makes sense and which satisfies point 1 and point 3. The question is, how do we find this charge assignment? Question number 1. And question number 2, why does this metric have not an horizon? Okay, so question number 1 is easily solved by using this holonomy condition, which I already showed to you for the spin 2 case. Okay, say no consistent charge assignment here. And now, using this holonomy condition, we generate a consistent charge assignment. And so the holonomy condition was that this omega which is 2 pi tau times AC plus tau bar AC bar, has eigenvalues 0 and plus minus 2 pi I. So in other words, this is equivalent to saying that the trace of omega, so which is just the sum of the eigenvalues, is 0. That the trace of omega squared is minus 8 pi squared. And the trace of omega cubed is also 0. So, and if you use these three equations, if you plug in your A and your A bar, which you got from the other side, use these three equations, then you get a consistent charge assignment. And to be honest, the charge assignment is consistent, and it's perfectly consistent also with the CFT side. However, it's not really illuminating, so therefore I don't write it down now. But what you get is a consistent charge assignment But if you put the functions L and W back again into the metric, then you realize metric has no horizon. And singularity. Has even no singularity. Okay. So, is it a black hole? And so at that point of view, at that point of time, basically, people approached us and said, okay, the solution you've written down is totally wrong. It's not a black hole. We don't believe that this is a black hole. But in higher spin gravity is tricky. I told you that we have these higher spin gauge transformations. And the higher spin gauge transformation, they act non-trivially on the metric and also on the spin-3 field. So in other words, the ds squared, the line element which you can compute from the metric, is no longer invariant under such a higher spin gauge transformation. In particular, using these higher spin gauge transformations, you can basically change your causality structure. And so what you can do is you can now find a gauge transformation. It is possible to find such a gauge transformation. So which brings my A and my A bar, so the ones which are associated with the small a and small a bar, to say an A tilde and an A bar tilde. And when now I take from this the metric and spin-3 field, is smooth at the horizon. So you have an horizon, you have a singularity at its smooth. So in other words, here, so this corresponds really to a black hole, which is asymptotically ADS. And here, we have no singularity, we have no event horizons. And they are connected by a gauge transformation. So, particularly, you can convince yourself so that this gauge transformation gives you the same physical object. And the nice thing is, by using this gauge transformation, we found that basically the charge assignment which we get is precisely the charge assignment. So the charge assignment So the temperature, say, and the chemical potential, and like the mass and the spin-3 field of that black hole is precisely the one which you calculated from the holonomy condition. In other words, the holonomy condition is a gauge invariant way to tell you, if I give you a gauge connection, whether you have a black hole or not. However, if you compute just your metric in your spin-3 field for this gauge connection, it does not necessarily have to look like a black hole. It could look like also in this way. So the lesson learned basically from the last 2 days is that the first, metric and spin-3 field are not gauge invariant. Second, this is what I've shown here, we can turn a wormhole into a black hole. So this is what we always call wormhole. And these are really the two the same objects, because what I can do is, if I go to Vasiliev gravity, and even like in Vasiliev gravity, these higher spin black holes are constructed, then you can calculate like correlation functions of scalar fields sitting here and here. And of course, then you can ask the question, is it really a wormhole or a black hole? Because they're such a scalar fields, they should realize, or they should see the nature of an event horizon or not. So what you can do is you can use this equation, which is above there, solve it, and really then see the causal structure. And also, if you have started with a gauge connection this way, what you see like the usual signs in the correlation function of a black hole. Okay? So the lesson is really, don't look just at the metric and the spin-3 field. In higher spin gravity, this might be completely, doesn't tell you anything. Look at the holonomy condition, which tells you if it's a black hole or not. The third one, which is also nice for this higher spin black hole, that the entropy is not given by the area of the it's not given by the area of the event horizon divided by 4 times the Newton constant. There are corrections to it. In other words, for the CFT people, there are corrections to the Cardi formula. And the fourth one is gauge invariant way. We have a gauge invariant way for black holes, a gauge invariant characterization of black holes, namely the holonomic condition. But now, since we can turn a wormhole into a black hole, and vice versa, the question really is, what is geometry? What is the notion of geometry in these higher spin gravity theories? They are very, very weird. And now we really need a new concept for this higher spin gravity theories to say something about what space-time. Because we can change the causality of space-time, and this is somehow weird. This is really a big question, which is not easy to answer, but which is the next one we should attack. It's definitely not the concept of a differential manifold. It has to be something generalized. And from ADS-CFT, we believe that we have something in our hands which might tell us something about the space-time geometry. And so this is the concept of entanglement entropy. So really in this higher spin gravity theories, at least for the spin 3 case, which we know which is dual to a conformal field theory, we can calculate the entanglement entropy on the conformal field theory side, which, if we know it not just for an interval, but like for different geometries, which might help us then to restore the background, the gravitational background, and in particular to get a notion of what space-time geometry is at the end. So I guess I should skip the presentation, or?
Yes.
Good. So let me end with a few open questions besides this one here. So these higher spin gravity theories are really interesting, as I told you in the beginning, because they might be related to string theory, in particular to the tensionless limit of string theory. And so first, we really should explore more this connection to see how these higher spin gravity theories are related to string theory. And this can be also done in an ADS-CFT context. In particular, we should establish like the precise mapping between the conformal field theory on the one hand side and the higher spin gravity theory on the other side. And with precise, I mean, we should not be only able to calculate interesting quantities on the CFT side from the gravity side, but also vice versa. We should be able to say something about the gravity side by just looking at CFT data. So why is this important? Because we only have a handle from the gravity side in a very special limit on the CFT side. So a very special sector of the CFT and a very special limit of the CFT is dual to this classical higher spin gravity theories. However, we can do calculations on the CFT side, not only for this particular sector and for this particular limit, but for the whole parameter space of the CFT. So what does the other basically regions of the CFT correspond to on the gravity side? They correspond to probably a quantum gravity version of Vasiliev theory. So in particular, we say something about quantum higher spin gravity. And so the question is, how do we get the space-time from the CFT data, for example? In particular, another question which is really interesting for me is, suppose now I look at, say, a black hole creation and black hole evaporation process in the gravity side. How is this encoded in the dual CFT? So what precisely do I have to look at the dual CFT? Can I calculate the same process just purely with CFT methods? And basically, can I say something about then the nature of quantum black holes just from the CFT computation? And let me again stress you, this in principle, we should be also able to do it for like ADS5 and CFT4, connecting like n equal to 4 superhanging modes with type 2B string theory, quantum type 2B string theory. However, this is a much more complicated duality. And we don't have both sides under full control. We cannot do a calculation purely on the gauge theory side at strong coupling. We cannot do a quantum gravity calculation or quantum string theory calculation. However, here with this higher spin gravity versus the CFT correspondence, so with this new correspondence, we have both sides, at least in the classical gravitational limit, under full control. And the CFT we even have in the quantum regime under full control. So we should really explore this kind of duality further, and at the end I hope to say something about the space-time structure, and in particular also say something not about the space-time structure of higher spin gravity, but the space-time structure of string theory. Okay, let's end with these very important but also very difficult open questions. Thanks.
So, are there any questions?
Can you please expand on why you found the lab diagram from wormhole? Because the wormhole black hole connection is been studied in other areas.
Yeah, so, okay, with wormhole, I just mean this kind of metric here, which we really get from the original gauge connection associated with A and A bar. Okay, so this here, the A and A bar I wrote down here, really presents the higher spin black hole. And if I calculate the metric, then I get something of this form where f of rho doesn't have a double zero. However, for rho going to plus infinity and rho going to minus infinity, we have two ADS spaces. So we have here a boundary and here a boundary, and something in between happens.
But no relation to, say, EPR specific?
We can discuss it further, because then I should have talked about entanglement entropy. Okay? I've got an idea which I can tell you. So. Yeah.
The connection for higher spin black hole, you just write it as the most general connection, or with some special?
Okay, so first, here I used again the so-called principal embedding of SL2 into SL3. If you do you can do the same thing also for the diagonal embedding, then you get a different class of black holes. Second, I also simplified here something, because for A we should have two independent charges, namely L and W, and for A bar we should have L bar and W bar. So this black hole is basically not rotating. That's basically just to write it down, I simplified it a bit. The generalization to a rotating black hole is known. Third, there's now a very recent discussion about in the literature whether this is a so-called W3 or W32 black hole. So it's referring to the asymptotic structure. And there was also a very recent new construction by Henault, Bunster, and a bunch of other people, like from April this year, who claim they found another class of higher spin black holes. So there's a lot of things to do. This is just for SL3. People constructed black holes also for SL4, SL5, and so on. People even started now constructing the black holes for the superalgebras, but in some sense this is only done on a case-by-case basis, so it's not looked at the kind of general features of such black holes. And most of the people, they just use the holonomy equation and they don't construct explicitly the gauge transformation to see that they really have an event horizon.